heat exchanger sample problem number 2. So for this problem, we are given with a double pipe. So we have shell and tube heat exchanger constructed with a stainless steel. The thermal conductivity is given, and the inner and outer diameter of the steel is also given as 1.5 cm and 1.9 cm, as you can see in the diagram. So this is a hollow tube with outer diameter of 1.9 and inner diameter of 1.5 cm. So the inner surface and the outer surface convection heat transfer coefficient for this steel is also given, as well as the fouling factor for the inner and outer part of the tube of the shell. So we are to determine the thermal resistance of the heat exchanger per unit length and the overall heat transfer coefficients UI and UO based on the inner and the outer surface areas of the tube. So our assumption for this problem is the heat transfer coefficient and the fouling factors are constant and uniform. So the second step is to establish the working equation for the thermal resistance. So from slide number 34, so the working equation for thermal resistance when fouling factor is present or will occur is in terms of this particular equation. So we concentrate first on this part of the equation and solve for the unknowns. So if you're going to look at this one, so our unknowns here are our area and area inside and area outside of this tube. So we will calculate as area AI and area AO for inner and outer part of the shell. So the inside area is given as pi diameter times the length. So since we don't have length, so we will solve for per unit length. So we will assume 1 meter as our length. That's why we have this area. Inside area, and for the outside area, we will use the diameter of the outside, which is 1.9 cm. So that's why we have 0.05969 meters squared. So we substitute all the present data that we have as well as AI and AO to solve for the thermal resistance. So that's why our thermal resistance is 0.0531 Kelvin per watt. So take note that the effect of thermal resistance is to decrease the heat transfer coefficient. So we need to, so this is related to the overall heat transfer coefficient. Related in the equation that we also saw in our working equations, and this time since we are to solve the overall heat transfer coefficients based on the inner and outer surface area, so we will equate the value of R, which is the same for inside and outside as given in this particular equation. So for the inside, so we can solve for UI in the inside by using this relationship. Rearranging this equation to solve for UI, and then substituting the values of thermal resistance, which we already solved, and the inside area. So the overall heat transfer coefficient based on the inside or inner area of the tube is 399.67 watt per meter squared Kelvin. We will use the same equation that we will just substitute for the outside area of the tube. So that's why we have 315.5 watt per meter squared Kelvin.